Hello everyone, welcome to Linear Model with me, Sarini Abdullah. Just a quick recall of what we have had in our previous video, that is, we learned the concept of whether the model is useful or not, and then what hypothesis that we need to test to say in order to know the usefulness of the model, how to calculate the test statistics, and then what is the rule to make a conclusion about our hypothesis. So in this session, we will just try to apply that concept to an example. Just a quick recall again, the model that we have is of this form, and then we say that the model is to be useful when this equation here is represented by a line that is not a horizontal line. Because when we have this horizontal line, it means that x is not contributing at all in explaining y, because it means that the model is just a constant, that is just yi equals beta naught. What we want to have is something like this, that is that beta 1 is not equal 0. It means that the slope of the line is not 0. So let's look at the example here. So then this is we run a simple linear regression using R package, and then in here we see that the model is that the fy tilde the fx. It means that our response variable is y, our predictor variable is x, and here we get the result here. So what do we have here? On the column estimate, we have the value of minus 2.069 and 3.378. So that is the estimated value of the intercept, that is the beta naught, or in our symbol is beta naught cap equals minus 2.069, and then our estimated value of beta 1 estimated using a sample data of size 34 is 3.378. How do we know that the sample size is 34? We look at here, the residual standard error is on 32 degrees of freedom, and we know that the degrees of freedom is the sample size minus the number of regression coefficient, and here we have two regression coefficients, that is beta naught and beta 1. So that's why we know that this result is estimated based on a sample of size 34. So then the question is that we want to know whether this line really explains or really represents the contribution of x in explaining y. And then based on the concept that we learned in previous video, it means that we need to test whether the beta 1 equals to 0 or not. Significantly different from 0, statistically or not. Okay, so here we get the calculated value of beta 1, the estimated value of beta 1 is given by 3.378. Mathematically speaking, this value is different from 0. But is it statistically different from 0? That's what we need to test. Okay, so from the procedure, to know whether this value is statistically significant from 0 or not, we do the t-test. Remember again in our previous video. So here we see that we have the t-value is 8.867. Is this value in the rejection region or is it in the acceptance region? In that case, we need to refer to the t-value and we take the significance level of 0.05, which means that this is our maximum tolerance level of making a wrong decision. So with the degrees of freedom of 32, we have the t-value for a two-test test is plus minus 2.0369. And then if we try to display the result in the t-distribution. So we have that minus 2.0369 is on the lower level, the critical value on the lower tail, and then plus 2.0369 is the critical value on the upper side of the upper tail. And then we see here our statistic test, our test statistic T is 8.867. It lies way beyond here. Okay, so it lies in the rejection region. In that case, we will reject our null hypothesis. Or we can just for simplicity, people usually just use the p-value here and compare it with the significance level. So here we get the p-value of 3.95 times 10 to the power of minus 10. It means that almost 0 is 0.00000 something. It means that this value is the area here. If we just continue this line, okay, so it means that this almost zero value represents that the probability of making a mistake in rejecting the null hypothesis if the null hypothesis is correct, that is X is not contributing in predicting Y. And since the probability is almost zero, okay, this is the area of this, what is it? Table or this distribution over here, since the probability is almost zero, way less than 0.05, then we will just reject the null hypothesis and we conclude that our X here is contributing significantly in explaining Y, because that beta 1 is statistically different from 0. Once we get that conclusion, then we are ready to use our result for interpretation and do the prediction. So again, we learned that model is useful when the explanatory variable can explain the target variable, and the model's goodness of fit is assessed by testing the slope of the regression line.